The objective of this video is to choose a binary encoding for a specific piece of information and justify those choices. So it probably sounds pretty complex, but basically you're going to take something in real life and try to create an encoding for it. That way you can better understand how encodings work in general. So to do so, we first have to talk about abstraction. Abstraction is the practice of temporarily ignoring details to focus only on the most significant or relevant portions of a problem. In the instance of binary information, we know that it's just a sequence of bits underlying even seemingly complex data structures, but we don't have to worry about that all the time. When you look at a program, when you are surfing the internet, you're not thinking about ones and zeros. Abstraction, the ability to rely on high-level encodings and temporarily ignore lower-level details, is the key to building the complex systems that we use and interact with every day. Think right here. Are you the type of person who can ignore the why of something and just push through the learning? I mentioned this at the beginning of the year and talked about the importance of being able to do that, because if you're always focused on the why, it's going to be really hard for you to get beyond just that lower level, that lowest level of ones and zeros. The course focuses so much on the digital representation of information because it is probably the most fundamental law of computing. So much of computer science is abstract, but it is all grounded in the laws and limitations of having to represent everything in binary. So no matter how high you go, Java is an example of a higher level programming language. No matter how high you go up in the tree, you still are working with ones and zeros, whether you know it or not. Internalizing this fact and internalizing the levels of abstraction that result, we believe is central to what makes a person good with computers or natural with them. Similarly, being able to take a high-level human idea and break it down into something that could be computed on is the fundamental essence of what it means to do computing work. Certainly, it helps a person explain and grapple with abstract computing ideas later on. For example, when programming, you have to manage complexity in code by breaking things down into smaller procedures. Think right here, what is a procedure? So, abstraction, a way of doing something right. You have to make many choices about how to represent and store the information your program needs. The person who implicitly understands the difference between choosing to use the number 5 instead of the character 5 is more likely to make the right choice. It's useful to practice the mechanics of producing a project like this on a tight timeline, especially one that includes both design and written elements. When you get older, if you have a job that requires you to do this, again, you'll be successful if you can differentiate between the number 5, the character 5, and if you're able to both design and write about what you're doing at the same time, or at least communicate verbally about that. Throughout the unit, we have been building layers of encodings on top of the foundation of bits. First, we learned to develop binary numbers. Then we did ASCII text, then formatted text, and finally black and white images followed by color images. High-level encodings are actually quite removed from the underlying bits from which they are made. So there's this giant gap from the ones and zeros to programming languages or encodings, okay? There's a huge gap between that. The distance is crazy. Try to name the 4 steps mentioned in the previous slide without looking, then check and correct. If you do mental checks like this during the test or during your creation performance task, I think it will help ground you to the level you're trying to work on. So let me help you with that and go back. First, we developed binary numbers. Step 1, learning about binary numbers. Step 2, ASCII text, and that connected to the binary because the number 65 is going to be the letter A. So step 2 was ASCII text. Step 3 was formatted text. Formatted meaning size, color. With the size we're going height and width, okay? Color and font, all these other things. That's the formatting of a text. And then with the black and white images and color images afterwards, you're looking at taking numbers and connecting them to colors of lights, pixels, right? And connecting that number with how bright a certain RGB value is going to be. So that was the fourth one. In your mind, walking yourself through this abstraction check should be very helpful, okay? We also saw this with the layers of internet protocols that we designed. The DNS protocol doesn't need to care or know how the bits are physically being transmitted to and from it, or even how the request is routed to it. That all has to happen, of course, but DNS only has to focus on the higher level task of mapping a domain to a number. So this layer of abstraction or level of abstraction is just specifically looking at taking a website's name, connecting it to an IP number. Think right, share. What is the job of the TCP IP protocols? If I just told you DNS's job was to map a domain name to a number, what is the job of TCP IP protocols? So it's called a protocol, not an encoding, because here's the step-by-step, not the binary, okay, it's the step-by-step. So the protocol is one thing happens and something else happens, and another thing happens and then something else happens. And encoding is more like a direct connection. The number 65 is directly connected to the letter A, and so on. So here we have a client computer talking to a server. The client sends a SYN packet, SYN standing for synchronization. The server acknowledges, acts to confirm inbound session open, and sends a SYN to established outbound connection. So now that you've established the connection, it sends information back. The client receives the ACK to complete inbound session. Then it sends another acknowledge to the server. Once a server receives that, it now has two sessions, inbound and outbound. Going over to the client sends chunks of data, the server confirms receiving that chunk of data, okay, and then it goes back and forth. Pretty easy. And then it will synchronize the end of the transmission. We could study how this protocol is encoded, but that is super deep, maybe graduate level study. I don't think we need all that. My question is, what limit does this protocol put on user data? And here's an image to sort of help you through that question. How user data is transmitted on the internet. So you have an IP header, so that includes an IP packet. You have TCP packet with a TCP header. These headers are just telling the computers what it's receiving, okay? And then, of course, in pink at the right-hand side, you're going to have the data of the thing. It could be text data, an image, a video, whatever data you're looking for will be there. And I thought it was interesting to acknowledge the number of bytes in each piece. I do not know how much the limit on user data is. Maybe it depends on what you're doing. But here's your challenge, extra credit. Go find out what your typical user data size is. TCP and IP headers are 20 bytes, at least 20 bytes. Figuring out clever ways to encode information is one of the things computer scientists need to think about in many different contexts. There was a time before we had digital images or music or streaming television or online shopping. Someone had to figure out how to encode those things in order to get them onto and into computing devices. For this project, you will design a way to encode some human experience in binary. Really fun project today. So this is an end of lesson challenge. I want you to do some individual research. We're about to do an encoding, and this is an oscilloscope you're looking at. Trying to get one of these for the school, at least one, so we can play around with it. So bonus, more extra credit right here. What is an oscilloscope? Okay, so now details on the challenge. You should choose any type of experience you wish. Your challenge is to identify the critical aspects of that experience and determine how that can be translated into a binary encoding. If you spent some time researching oscilloscope, you're going to walk away with some more knowledge how the wires on electrical devices can be read directly so you can see those ones and zeros in real time. So your task is to pick a general category of experience. So like going to a baseball game is a general experience, as opposed to a specific game you attended, right? Don't tell me about the Yankees and the Astros game. Pick something that isn't already digital, so going to a concert is a better choice than making a playlist. Since the second one is already primarily a digital process, making a playlist is something you can already do on a computer. I want you to think about an experience that is not already done on a computer. Pick something you have a detailed understanding of, like walking on the moon is fun if you think you know enough to design that, but walking to school has a lot of interesting information as well. So make sure you pick something that you know a lot of details about. And here's the DOL. You're going to pick something and explain how it's a general experience, so you're proving it. And number 2, not already digital, but could be something you have a detailed understanding of. So kind of explain to me what those details that you understand are. And this is going to set us up for tomorrow's lesson, where we actually start the encoding process. So this is like day 1 of the whole encoding experience.